Thank you. The most important thing to tell you about this talk is that I'm not at all sure what I'm going to be saying is correct. I considered whether it was therefore my duty to cancel the lecture. It was tempting. But I justified giving the talk to myself on the grounds that you might learn something from what I was trying to do, even if it turns out that my proposal isn't right. So we're going to be talking about three-dimensional pure quantum gravity with the Einstein-Hilbert action that I've written in terms of Newton's constant and the cosmological constant, which has been written as 2 over L squared. And it's a very tempting problem to study because three-dimensional gravity classically is said to be trivial. Nothing happens. The Einstein equations imply that depending on the sign of the cosmological constant, every solution is locally equivalent to either de Sitter space, Minkowski space, or anti-de Sitter space, depending on whether L squared is positive, negative, or 0. So since it's trivial classically, it's reasonable to hope that you at least might be able to solve it quantum mechanically. And maybe you'd be able to learn something from the exact solution. So it's been studied from many points of view by people who hoped to, in this way, get a soluble model of quantum gravity, but nevertheless, the status is fundamentally unclear. Now, the main reason that I've chosen to look at this problem again is something called the BTZ black hole, Bagnatos, Teitelboim, and Zanelli, introduced in around 1992. When the cosmological constant is negative, there are black holes in 2 plus 1 dimensions, not when it's 0 or positive. Now, since pure gravity in 2 plus 1 dimensions is trivial, meaning that it has no propagating modes, no gravitons, we might hope that we could solve it, and thereby get an exact description of a quantum theory with black holes. In 4 dimensions, it's hopeless to get a precise description of quantum mechanics with a black hole because the 4-dimensional phenomena are far too complicated. But in 3 dimensions, you could at least possibly get a precise black hole model. Now, you might also conceivably do it in 1 plus 1 dimensions, but 1 plus 1 dimensions is less realistic because the black hole horizon only consists of 2 points. And the basic property of the Bekenstein-Hawking entropy that's proportional to the area or perimeter of the horizon is lost in 1 plus 1 dimensions. In 2 plus 1 dimensions, there are black holes that are like holes in 2-dimensional space. They have a perimeter, and they have a Bekenstein-Hawking entropy proportional to the length of the perimeter. So it's a much more realistic model for black holes, if you could solve it. Now, the first observation, well, the 0th observation about this theory is that by power counting it's unrenormalizable because Newton's constant has dimensions of length in 3 dimensions, a negative power of mass. So by power counting, this is an unrenormalizable theory. However, in perturbation theory, it's actually finite, modulo field redefinition and a renormalization of the cosmological constant. That's so for the same reason that the theory is trivial. After all, it should feel funny to claim that a trivial theory is unrenormalizable. In 2 plus 1 dimensions, the Riemann tensor can be expressed in terms of the Ricci tensor, which in turn, using Einstein's equations, can be expressed in terms of the metric tensor. These are the steps that are used to prove that the theory is trivial. So finally, on shell, the only possible counterterm is the volume of space-time, that is a renormalization of the cosmological constant. What I've just said is true no matter how you do perturbation theory, but there's actually a natural formulation in which no normalization or field redefinition is needed. This comes from the fact that classically, 2 plus 1 dimensional gravity can be expressed in terms of gauge theory. The spin connection omega is an SO21 gauge field. And it can be combined with the Fierbein E to make a gauge field of a group SO22 if the cosmological constant is negative. There's a similar story if the cosmological constant is 0 or positive. You just combine omega and E into a 4 by 4 matrix where there's a 3 by 3 block and E is in the last row and column. And then a small calculation shows that as long as the field line is invertible, the usual transformations under local Lorentz transformations of diffeomorphisms combine together as gauge transformations of A. What I've said so far is true in any dimension, but there's something crucial which is only true in 3 dimensions. What's special in 2 plus 1 or 3 dimensions is that not only can you combine the fields and the gauge symmetries into gauge transformations of a gauge field A, but you can also write the Einstein-Hilbert action in a gauge invariant form as a Chern-Simons interaction, where trace is a certain invariant quadratic form in the Lie algebra, not the obvious one. Now, in the Chern-Simons description, the coupling constant has suddenly become dimensionless. The unrenormalizability has disappeared back here. Actually, I left it out, but there's a 1 over L in this formula. So the bad dimensional analysis disappeared in the change of variables. And now, it's a superficially renormalizable theory, but it's not just renormalizable, it's actually finite in perturbation theory, since there are no possible local counterterms. In general, in quantum field theory, infinities have to do with gauge invariant local counterterms, but in Chern-Simons gauge theory, there aren't any. One way to say it is that since the field equations are that the curvature vanishes, any local counterterm is 0. So classically, we can re-express three-dimensional gravity in terms of gauge theory. Now, quantum mechanically, it's not totally clear that this is valid because we assume the field line to be invertible, and it's not totally clear we're allowed to assume that classically. But this transformation was valid classically, and therefore it's valid in perturbation theory, because perturbation theory is infinitesimally close to the classical description. Perturbation theory won't take us out of the classical region where the field line is invertible. But non-perturbatively, there's a real question. As in gauge theory, we'll have to allow the field line to not be invertible. My own view when I first worked on this was that the gauge theory description was correct non-perturbatively, and one had to allow a degenerate field line to make sense of the quantum theory. That still might be correct, but it's been criticized fairly convincingly, although I don't really want to go into the arguments. But although there's a variety of technical objections, there's something that to me is a more serious problem with the claim that gravity equals gauge theory non-perturbatively in 3 dimensions. And this has to do with something I already told you about, the BTZ black hole. At some point it was appreciated that for the case of negative cosmological constant, there's a black hole in this supposedly trivial theory. And that actually makes the theory much more interesting. I think that the main reason it's interesting to try to solve it is, as I said before, that you could possibly get a model of quantum black holes. And moreover, subsequent developments involving the correspondence between anti-de Sitter space and conformal field theory made it clear that the BTZ black hole should be taken seriously. Now, as I actually already mentioned, the BTZ black hole has a horizon of positive circumference and a corresponding vacancy in Hawking entropy proportional to the circumference. And therefore, if there is a quantum theory corresponding to pure 3-dimensional gravity, it ought to have a huge degeneracy of black hole states. And in my opinion, we're not going to get them in a reasonable way from topological field theory, though some attempts have been made. And in fact, there's a substantial community of people who are very enthusiastic about trying to do it. But it looks like an uphill battle. Now, before going on, let's discuss what we're going to aim for in trying to solve 3-dimensional gravity. What would it mean to succeed? Well, first of all, we're only going to consider the case of negative cosmological constant. Well, there's some suspicion that quantum gravity with positive lambda doesn't